Representation distribution matching for one-step visual generation. That is the paper we're looking at today. And I mean, it is absolutely wild. So typically one-step generation requires really expensive trajectory distillation.
Right. Or constantly querying online teachers, which takes forever.
Exactly. But this paper proves that you can train a one-step model directly. Like you just match the feature distributions across a diverse battery of frozen encoders.
Yeah, and they do this by fixing how we estimate maximum mean discrepancy, or MMD, using this Nyström approximation, which is brilliant.
It really is. They balance multiple encoders, and the resulting model, which they call iRDM, just completely crushes the previous state of the art. It hits a 1.3 on their new SWR14 metric.
And get this, they even post-trained a four-step FLUX 0.2 model into a one-step model in just 90 H200 GPU hours.
Right. And the one-step student actually beats the four-step teacher. It's crazy. Welcome, everyone, to AI Paper Slop, the series where we summarize the latest AI and tech papers for you, the technical folks who want to stay on the cutting edge. Okay, let's unpack this, because getting a model to map pure noise to a high-fidelity image in a single forward pass without following a teacher's trajectory, I mean, that fundamentally changes the game.
It really does. It forces us to reconsider, the entire computational pipeline we've just sort of accepted as mandatory for generative AI.
Yeah, totally. But to understand the mechanics of RDM, representation distribution matching, we really first have to look at why we ever use trajectories in the first place, right?
Yeah, exactly.
Yeah.
Because generative modeling is, at its core, always about distribution matching. You have a complex distribution of real-world data, so photographs of cats, cars, landscapes, and you want your neural network's output distribution to map precisely onto that real data.
Right.
But diffusion models only do this implicitly. They learn the vector field of a noise distribution, and they simulate a denoising trajectory, step by step, until they land in the real data manifold.
And distillation methods are really just trying to speed that up, right? Like taking larger steps along that exact same simulated path.
Precisely. But RDM discards the path completely. The network just evaluates once. It maps a noise prior directly to an image. No trajectory, no ODE solvers, no online teacher network feeding it targets during the training loop.
The analogy I keep coming back to is navigating a city. So standard diffusion is like following a GPS turn by turn. You calculate every block, make every single turn.
Right.
And distilling it just means you're trying to skip a few intersections, but you're still bound to the street.
Yeah, exactly.
But RDM is like instant teleportation. You input the coordinates and you just appear at the destination. But here is my immediate issue with that premise. If you can just teleport, if you can just look at the feature space of a frozen encoder and match the real distribution, why were we bothering with the turn-by-turn navigation for the last 5 years?
Well, because the theory of teleportation is easy, but the math of calculating those exact destination coordinates in a high-dimensional space is extremely difficult.
Yeah, I imagine.
The authors highlight that previous attempts failed because researchers couldn't optimize two critical design axes. The first axis is the mathematical comparison, like how do you actually calculate the discrepancy between your generated distribution and the real distribution.
Right.
And the second axis involves the representations themselves, like which feature spaces are you actually performing this calculation in.
Okay, let's start with that first axis, the mathematical comparison. When I saw the authors were using maximum mean discrepancy, MMD, I honestly assumed it was a typo.
Yeah, a lot of people probably did.
I mean, in the early days of JANs, MMD was tested and just abandoned. It simply couldn't produce high-resolution competitive images because, well, the gradients it provided were just way too weak, right?
Right, but what's fascinating here is that MMD's perceived weakness wasn't a flaw in the objective function itself. It was a flaw in how we estimated it.
Oh, interesting.
Yeah, so if you look at the mechanics of MMD, it calculates the distance between the means of two distributions in a kernel-induced feature space.
Oh, okay.
To do that accurately, you need a massive amount of samples from both distributions. If your batch size is small, the calculated mean fluctuates wildly.
Which injects noise into your gradient and the optimization just stalls out.
Exactly.
Which makes sense. I mean, if you pull, say, 16 random images from a data set of 1 million images, the quote-unquote mean of those 16 images is not going to accurately represent the entire data set. It shifts every time you draw a new batch.
Right. It's way too noisy.
So how do they stabilize it without, passing 1 million images through the GPU on every single step?
Well, they recognize that the two distributions they're comparing have entirely different constraints. The real data distribution, the target, is static. It never changes.
Okay.
So rather than sampling it in small batches during training, they just pre-process the entire 1.28 million image dataset in advance.
Wait, but you can't just load 1.28 million high-dimensional feature vectors into memory during a training loop. That would melt the cluster.
You definitely can't. And this is where the Nyström approximation comes in.
Yes, I want to dig into that because the paper says they used a Nyström kernel mean embedding to compress the real dataset into 4096 landmarks. Conceptually, how does that compression even work without just destroying the shape of the data distribution?
Think of the full data set as a massive, sprawling continent of data points. Calculating your distance to every single grain of sand on that continent is mathematically intractable.
Right.
The Nyström method allows you to find a representative subset, those landmarks, that mathematically approximate the full kernel matrix. It's akin to finding the sort of gravitational centers of various semantic clusters within the data.
Oh, wow. So they're like anchor points.
Exactly. And because they use a kernel mean embedding, these 4096 landmarks act as a zero variance, fixed summary of the entire 1.28 million images.
So the attraction term in the MMD lost the force that's pulling the generated images toward reality that costs almost zero compute during the actual training loop. It's just a frozen static reference point.
Yep, completely static.
But the other side of the equation, the generated images that's constantly shifting as the model updates, you obviously can't freeze that.
No, you cannot. The generated side must be drawn fresh on every single forward pass. And remember, MMD doesn't just calculate attraction, it also calculates repulsion.
Repulsion, like keeping the generated images away from each other.
Exactly. It calculates the distance between the generated samples themselves to ensure they don't all just collapse into a single identical image.
Mode collapse.
Right. And to get an accurate estimate of this within-batch repulsion, your batch size needs to be enormous.
And this is where the hardware limitations usually hit a brick wall. To get that exact within-batch repulsion against the Nyström reference, they scaled the generator's batch size to 5120, and for some runs, all the way to 1,240.
Yeah, massive batches.
I look at those numbers, and I look at a 4 billion parameter model like FLUX, and the math just doesn't compute. You literally cannot fit 10,000 high-resolution images and their gradients into VRAM simultaneously.
You definitely can't. But you don't need to hold the activations for all 10,000 images at once if you implement gradient caching.
Okay, let's break down how that caching actually functions, because it seems like a cheat code for memory constraints.
It really is. It leverages the chain rule. So the MMD loss function ultimately operates on the pairwise distances between the generated features.
Okay.
What you can do is run the forward pass in much smaller microbatches, say 32 images at a time.
Which is very manageable.
Right. You extract the features, calculate how those features contribute to the overall MMD gradient, cache those specific gradient values, and then you just discard the heavy image activations from memory entirely.
Oh, wow.
Yeah, and you sequentially accumulate these gradients across the entire 10,000 image batch. Only after the full batch has been processed do you execute a single backward pass to update the model weights.
So you're basically trading compute time for memory. It takes slightly longer to run the steps sequentially, but it allows you to construct a mathematically exact repulsion matrix for 10,000 images, which gives you a razor-sharp gradient without melting your GPUs.
Exactly.
Okay, so that solves the comparison axis. We have a completely stable math foundation now. But, I mean, calculating distances perfectly is totally useless if you're calculating them in a flawed dimension. Which brings us to the second axis, the representations.
Right, because feature distances are the standard currency for evaluating realism. The most common is Frechette inception distance FID, which measures the gap between distributions inside the feature space of a single ancient inception V3 network.
Yeah, everyone uses FID, but the generative AI community has known for a while that relying on a single encoder is a really fragile proxy for how humans actually perceive images.
It's extremely fragile.
And here's where it gets really interesting. The authors ran an ablation study to demonstrate just how fragile it is, and the outcome is highly revealing. So you might assume that inception is just outdated, right? And if we just swap it for a modern, highly semantic vision transformer like Dino V2, the problem goes away.
That would be the intuitive guess.
Right. So they trained a model to explicitly minimize the MMD distance using only the Dino V2 feature space. And mathematically it worked. The generator drove the distance score down to 1.01, which is effectively the exact same score achieved by real held-out validation photos.
Yeah, so if you blindly trust the metric, you would conclude the model had achieved total photorealism.
But visual inspection tells a completely different story. They show a generated image of a lizard sitting next to a typewriter. And the lizard looks fantastic. The scales, the lighting, everything is just totally photorealistic.
But the typewriter is a complete disaster.
Exactly. The keys are mangled, they overlap in impossible ways, the geometry is totally alien. Yet Dino V2 looked at that typewriter and scored it as perfectly real. Why does a state-of-the-art vision model fail to recognize such an obvious structural failure?
Because every neural network has blind spots based on its architecture and its training objective. Dino V2 is a self-supervised model heavily biased towards semantic clustering and texture.
Okay, so it cares more about the stuff than the shape.
Right. It prioritizes recognizing that an object is made of metal and plastic over verifying the strict, rigid geometry of a mechanical keyboard.
That makes a lot of sense.
So when you place a generative model under intense optimization pressure against a single metric, it behaves like water finding a crack in a foundation. It exploits the blind spot. It minimizes the loss by perfecting textures while completely ignoring structural coherence.
It's reward hacking in its purest form.
Exactly.
So the authors conclude that a single metric is mathematically insufficient. Their solution is to construct a battery of 10 different frozen encoders. And they didn't just pick 10 similar vision transformers, they specifically selected models that fail in distinct ways.
Yeah, they wanted a very diverse panel. They included self-supervised models, language-supervised models like CLIP and SIGLIP, multimodal autoregressive models, and generative autoencoders.
And they conceptualized this using the weakest stave rule.
Yes, the barrel analogy. Imagine a wooden barrel made of vertical staves of varying lengths. The barrel can only hold water up to the height of its shortest stave. Human visual perception operates on a very similar principle. We judge an image by its most glaring artifact. The lighting might be perfect, but if the subject has 3 arms, the image is fake.
Yep, the illusion is broken instantly.
By using 10 diverse encoders, they ensure that if the generator tries to hack the texture space, a structurally focused encoder will flag the structural anomaly.
I see the logic there, absolutely, but the optimization math seems kind of tricky. If you have 10 different loss values from 10 different encoders and you just average them together, won't the optimizer still take the path of least resistance?
What do you mean?
Like, if fixing the typewriter geometry for CLIP is mathematically harder than improving the lizard scales for Dino V2, an average loss function will just keep improving the lizard because it's computationally cheaper, right?
That is exactly what happens with uniform averaging. To prevent this, they frame the encoder weighting as a constrained optimization problem and solve it using a proportional Lagrangian controller.
Okay, wait, let me see if I have an intuition for this. If I'm operating a live audio mixing desk, right, and the bass track starts clipping, I instinctively pull the bass fader down to balance the overall mix. Is the controller doing something similar with the gradients?
Your analogy is close, but the controller's logic is actually inverted.
Oh, really?
Yeah, you aren't pulling down the loudest signal. You are dynamically routing power to the weakest link. The controller monitors the current MMD score for each of the 10 encoders. And crucially, it knows the floor for each encoder, basically, the score that real validation data achieves in that specific feature space.
Okay, so it has a baseline of what real looks like for every single model.
Exactly. At every step, the controller calculates how far each encoder is from its target floor. It then dynamically adjusts the learning weights, pouring the highest percentage of the training budget into the encoder that is currently the furthest away from reality.
Oh, I see. It sets a dynamic satisfaction gate. So if Dino V2 reaches the baseline score of real data, its weight just drops to 0. The controller tells the optimizer, Dino V2 is happy, stop allocating resources there. But CLIP is still detecting mangled typewriter keys, so route 100% of the gradient budget into fixing the flaws that CLIP sees.
It creates a brilliant self-balancing anti-overfitting mechanism. The optimization weights only vanish when all 10 diverse representations are satisfied simultaneously.
Wow.
Finding an adversarial loophole across 10 distinct architectural paradigms simultaneously is astronomically more difficult for the generator than gaming a single metric.
Yeah, that elegantly solves the unconditional image generation problem. We have exact MMD through Nyström compression, gradient caching for massive batches, and a dynamically balanced 10 encoder battery.
Yep, the foundation is solid.
But the real utility for ML engineers today is conditional text-to-image generation. I mean, if I prompt the model for a red car and it generates a mathematically flawless image of a blue boat, the realism metrics might look great, but the model is completely useless.
Right, alignment is everything.
So how do they force text alignment without breaking the mathematical elegance of the RDM framework?
This highlights the tension between the image marginal distribution and the joint distribution.
Okay, break that down.
Sure. So many generators match the image marginal, meaning they ensure the distribution of generated pixels matches the distribution of real pixels.
Meaning it looks like a real photo.
Exactly.
Yeah.
But the connection to the conditioning text can drift. iRDM shifts the objective to match the joint law of the image and the caption.
So they are basically concatenating the data. You take the visual features from the 10 encoders, and you mathematically staple them to the text embeddings.
That is exactly the mechanism. They couple the visual feature vectors with frozen SIGLIP text embeddings. The kernel isn't just comparing images anymore, it's comparing joint pairs.
Okay.
So a reference pair is a real image coupled with its ground truth caption. And a generated pair is a generated image coupled with the user prompt.
I want to make sure I understand the causal effect of that concatenation on the MMD loss. Because the kernel is measuring the distance between these combined vectors, prompt fidelity becomes a non-negotiable requirement of the math.
Precisely.
If the model generates a realistic blue boat for a red car prompt, the image vector might look perfectly real on its own, but the combined image text vector will be mathematically distant from any real image text pair in the Nyström reference.
Correct. Under the joint kernel, the generated output is pulled specifically toward reference points where the visual content and the semantic meaning of the text are perfectly aligned.
That's incredibly smart.
Yeah, the model cannot simply memorize high-frequency textures anymore. It must learn the semantic bridge between the text condition and the pixel output to minimize the distance.
The theory is just incredibly cohesive, but obviously we need to look at the empirical results. To prove this actually works, the authors had to introduce a metric that couldn't be gamed. Because if you train on an ensemble of 10 encoders, you can't just run an evaluation on one of those exact same encoders and claim victory.
No, the evaluation requires the same adversarial robustness as the training loss itself. So they introduced SWR14, which stands for Sliced Wasserstein Ratio, averaged over 14 different encoders.
And 4 of those encoders are entirely held out from the training process, right? To test for true generalization.
Exactly.
And the choice of Sliced Wasserstein is deliberate. I read that it's an optimal transport metric, meaning it is mathematically orthogonal to the kernel MMD they used for the training loss. Why does that matter so much?
It matters because it prevents metric contamination. If they used an MMD-based metric for evaluation, the generator might score highly simply because it learned to exploit the idiosyncrasies of kernel mean embeddings.
Right, another form of hacking.
Yeah, but Sliced Wasserstein operates differently. It projects the high-dimensional feature distributions into 1D lines and calculates the cost of transporting the generated distribution mass to match the real distribution mass.
Okay, so it's a completely different way of measuring the gap.
Exactly. Because the underlying math is completely independent, a high score on SWR14 is a strong indicator of genuine distributional alignment, not just reward hacking.
And the results speak for themselves. The baseline score for real, held-out validation photos on SWR14 is 1.0. Prior to this paper, the state-of-the-art for one-step generators was sitting at 2.05.
Yeah, pretty far off.
But iRDM completely shattered that baseline, hitting a 1.30. They nearly halved the discrepancy between generated and real data.
And the robustness of the SWR14 metric is validated by how well it correlates with human perception, which is really the ultimate test. When they evaluated iRDM against prior state-of-the-art models using PIC-score, which is a heavily optimized proxy for human preference, the results were highly disruptive.
Disruptive? How?
The one-step iRDM model wasn't just preferred over other generators, it was preferred over real, held-out photographs 63.6% of the time.
Wait, let's pause on that statistic. Over 60% of the time, the evaluation model analyzed a real photograph and an iRDM-generated image and concluded the generated image was a better, more accurate representation of the text prompt. That level of alignment from a single network evaluation is just difficult to overstate. Which brings us to the application phase. How does this pure mathematical framework translate to the massive multi-billion parameter foundation models dominating the ecosystem right now?
Well, the authors designed a post-training experiment to prove the scalability of the joint objective pipeline. They targeted the FLUX.2 Klein model, which is a highly optimized 4 billion parameter Four-step generator.
Right. And rather than spinning up a complex adversarial network or running expensive ODE solvers for distillation, they utilized the RDM approach. They generated a curated reference set of about 300,000 images using the original FLUX model as a teacher.
Yep. They verified the compositional correctness of these images, compressed them into the frozen Nyström reference, and then initiated the post-training process.
And the efficiency of this process is the critical takeaway for ML engineers listening to this. The teacher model is only used once to generate the static reference data set.
Right, just once.
During the actual post-training phase, the teacher is completely absent from VRAM. The post-training required only 180 optimizer steps at a batch size of 2240.
It required just 90 H200 GPU hours to convert a four-step state-of-the-art model into a one-step model.
I mean, in the context of foundational model training, 90 GPU hours is essentially a rounding error. It's nothing.
It is nothing. And the performance metrics suggest the one-step student actually outperformed the four-step teacher. On the Generative benchmark, the one-step iRDM scored 0.826 compared to the teacher's 0.794.
Wow. Where did it improve the most?
The specific areas of improvement are really revealing. The one-step student demonstrated significant gains in complex compositional tasks specifically, to object positioning and attribute binding.
Like making sure a prompt for a red car in a blue sky doesn't bleed the red into the sky.
Exactly. This confirms that the joint image text coupling within the RDM framework enforces semantic alignment far more strictly than standard trajectory distillation ever could.
So, to pull it all together, we have a framework that combines an exact within-batch repulsion, a frozen Nyström compression to stabilize the target, gradient caching to support massive batches, and a dynamically balanced 10-encoder Lagrangian controller to eliminate reward hacking.
It's quite the list.
They bypass the step-by-step denoising paradigm entirely and achieve state-of-the-art results. It's just phenomenal work.
It really is. And, this raises a fundamental question for the broader AI research community. We have just examined a methodology representation distribution matching that leverages frozen, off-the-shelf vision encoders to achieve incredible results.
Yeah.
But the underlying mathematics of kernel embeddings, MMD, and Lagrangian controllers are completely modality agnostic.
Oh, wait.
Yeah. If you have a robust pre-trained encoder for audio or video or complex robotic control sequences, you can compress that real data into a Nyström reference and train a one-step generator for that modality.
Wow, so this could go way beyond images.
Exactly. It forces us to ask, does this mathematical framework signal the beginning of the end for step-by-step diffusion scaling across the entire AI ecosystem?
I mean, if the math allows us to teleport directly to the optimal destination coordinates in a single step, the rationale for spending compute on turn-by-turn trajectory simulation becomes very, very difficult to justify. It is a massive shift in generative architecture.
Well, thank you all for tuning into this deep dive on AI paper slop. We know your time is valuable, so we hope this breakdown helped you parse the signal from the noise. We'll catch you on the next one, where we keep unpacking the future, one paper at a time.